Welcome everyone. Thanks for attending to my presentation. My name is Mario Alberto Rico from CIMAP Monterrey, and I'm going to be talking about the effect of oxygen source on the various properties of tin oxide thin films deposited by plasma-enhanced atomic layer deposition. As an introduction, tin oxide has been widely used as electron transport layer in perovskite solar cells. Also, tin oxide has high electron mobility, wide band gap, around 3.6 electron volts, and has high transparency in visible range. On the other hand, atomic layer deposition has a highly reproducible thin films deposition tool, because the deposition of the thin films can be controlled at subnanometric scales. In this slide, you can see the experimental details, where three different substrates of silicon, glass, or FTO were cleaned with three different solvents in an ultrasonic bath for 15 minutes in each step. Then were drying with a nitrogen flow. After that, the substrates were cleaned with ozone during 15 minutes. Next, tin oxide thin films were deposited on the different substrates by atomic layer deposition. And finally, all films deposited were characterized. In this slide, you can see the different synthesis condition of tin oxide by atomic layer deposition and the different group per cycle for each condition. Also, we can see that there is an effect of oxidizing source in the growth per cycle. Next, we can see that in about experiments, the growth per cycle is bigger using water at 80 degrees Celsius, and at 200 degrees Celsius, the nucleation and growth events are directly influenced by temperature. The surface chemistry and binding states of tin oxide thin films were determined at 80 degrees Celsius on fluorine tin oxide. The spectra were adjusted using void peaks and the Shirley-Shewood background, and showed that exists a dependence on the chemical characteristics on surface depending on the oxidizing agent. In addition, if we observe the carbon and oxygen signals, there is a dependence on the amount of impurities according to the oxidizing agent. Optical properties were made on tin oxide films on glass, and they have high optical transparency, around 80% in the visible region. This is good because they can be used as whole transport layer in perovskite solar cells. In addition, all films have a bandgap around 4.6 electron volts, which was determined with the Taux relation. Surface topography analysis was performed with atomic force microscopy on films grown at low temperatures, and they don't show a clear difference in the oxygen source. Furthermore, there is no clear effect on surface topography. Electrical properties were made on tin oxide thin films grown at 200 degrees Celsius on glass using 4-point method. These films show low resistivity, around 3 times 10 to the negative 4. Meanwhile, the resistivity and resistance shed are related to the defects on the surface in the ALD films. Then, Hall effects measurements were made to check the values obtained by 4 points, where the values obtained by 4 points were verified. After that, the values of resistivity, mobility, and carrier concentration were related to the best reported. Furthermore, these values are attributed to surface defects. Finally, the conclusions are: number 1. There is a high dependence of growth per cycle with oxygen source. Number 2 is exists a relation between the growth per cycle and the synthesis temperature. Number 3 is the synthesis at 80 degrees Celsius have more contamination on surface than at 200 degrees Celsius. And number 4 is chemical characteristics affect directly on electrical properties, and this was checked with XPS measurement, 4 points probe, and Hall effect. Number 5 is all films have high optical transparency, which makes them suitable for an electron transport layer. And number 6 is all films have low resistivity, high carrier concentration, and this is attributed to the optimization of the position parameters.